today's going to be our last part on data streams analytics. We're still going to be thinking about data streams, but from this point on, it's going to be more on the architecture and programming side. We might get to implement some of these at some point, but let's see. So what are we going to do today? We're going to be wrapping up streaming analytics with two problems. One is kind of a very simple one. Anyway, here is what we want to do. We want to be counting the number of distinct elements in a stream. So let's imagine that we have a data stream, and we know that in the entire universe, let's get this set aside here. But what we want to maintain is a count of the number of distinct elements so far. What I'm thinking about is the fact that as you observe a stream, you're going to be seeing, well, maybe A shows up, you're going to be seeing B shows up, you're going to be seeing C shows up, maybe A shows up again, B shows up again, and C shows up again, right? The thing is, even though the length of the stream currently is 1, 2, 3, 4, 5, 6, right? But if you count the number of unique distinct elements, what you're seeing is that the formula set A, B, and C. So the count of the number of distinct elements right now is not 6, right? So if you have to solve this problem, what is an obvious solution? A set. So keep a hash table or a hash set of some kind. Well, maybe not hash, a tree set, a tree map or whatever, right? So you can actually accomplish this using a method to keep a set of distinct elements that we're going to see so far. How much space are we talking about with this obvious approach? Space? How much? Order of? Where n is what? So I'm going to be using m for the number of distinct elements. And this makes sense because the size of distinct elements that we've seen so far is determined by how many distinct elements we have, right? And that's all that we have right now. In terms of application, where you should care about this, maybe you could be tracking on web pages. Like you're crawling a website, you're looking at many of them at the same time, and you want to find how many different words you have. This could be a very quick way to tell whether this page is real or it is a scam, because when the count is so low or when the count is super high compared to the number of words in there, it could be a signal that this is a scam. What else might we use this for?
Wait, I'm going to confuse you about example. If there's only a few unique words that's indicative that it's a scam page.
Usually what you do is you use that as a first cut signal, meaning maybe you count the distinct word compared to the number of words. What percentage?
Okay.
Typically, if you have a legit page, that should be in some range.
Gotcha.
Yeah, too low or too high, that signals a problem. Or you can do something as silly as how many different web pages does this particular customer request in a week. And you might be tracking multiple customers. Or you might be tracking, you are an ISP, internet service provider, and you might be tracking something like that. Okay, enough for applications. The question that I have for you guys is there a way for us to track the number of distinct elements using fewer space, less space than linear in the number of distinct elements? Because the real problem, at least in practice, oftentimes is we don't have enough space to maintain that set of elements. So you want to be tracking this in the so-called sublinear space region. And we're going to be okay if some error comes up. as long as it is reasonable. So we're going to be okay with the error of the form. The count that we have is within 2% of the true distinct count, with probability at least 95%. Something like that, right? And that's the kind of algorithm that we're going to be seeking. The algorithm I'm about to show you is a crossover between two papers, FM85 and AMS96, both very influential in the streaming literature. The idea is super simple. We're maintaining just two things. Number one, a variable known as min hash. If that makes you cringe somehow because of some other context, it is a different min hash, but it happens to be the same thing. And then you also have to keep another thing around, and that is a hash function. This hash function takes an element and then it's going to produce a number between 0 and 1. This is a good time to mention one crucial but rather dumb property of a hash function. If I fix a hash function, the first time I see A, if the hash function says 0.05, and I go on and process B, and go on and process C, when I see A again, what value is H going to return? Is it always going to be this guy, or is it going to be something different? So, what do you think?
I think it always be the same.
It will be the same, right? So a hash function generates a seemingly looking random number, but it has consistency inside. Meaning, when you see the same element again for the second time, third time, you're always going to get that same random value. Okay, so that's going to be a crucial property that we're using here. For process, just to keep things simple, we're going to be taking in a new element. This guy is going to be known as I. What is going to happen here is I'm going to hash that thing. So what do I get? When I hash that thing, I'm going to get a number. What range? Between 0 and 1. If this number happens to be smaller, then they're going to be hash. Being hash is replaced with this new number. The slide has a typo, but basically I'm talking about this process. Where is my animation? So, first time I witness 2, I see hash of 2. It's going to show up here. And this is on the number line, so 0 is here, 1 is here. And then the second thing that shows up is probably some other number, 5. Note that even though 5 is bigger than 2, the hash of 5 doesn't have to be bigger than the hash of 2. So 5 shows up here right now. Right? So we're going to keep doing this for all the elements that we observe. Eventually, what's going to happen is we are going to track min hash. This is the minimum, right? The point is, if I want to know how many distinct elements we have seen so far, this is what I want to output. 1 over min hash minus 1. That sounds really strange as a process. But the reason this works is if some element I repeats itself multiple times, the hash function is always going to return that same value, so it doesn't affect min hash, right? And if you revisit down and work out the math, the expected value of min hash, actually this is a simple integral, you can do it at home if you want to. Turns out to be 1 over m plus 1, where m is the number of distinct elements in your system. Okay? So this weird looking formula comes from basically we just want to solve for m in this equation. Because min hash is in hash. And we just wanted to know what n is. Now, for most of us in this room, we kind of realize that expectation is not what actually happens in reality. Unless we have a bunch of them and we get some sort of concentration of measure or the central limit theorem phenomenon type thing. So, I want to talk to you about two things, an upgrade to this process. Oh, by the way, how much space are we talking about right now? What is it here? What are we keeping track of? According to this algorithm, what are we keeping track of? The pseudo code is right here. So if you implement this as a program, what are your member variables in the class? Only in hash. Anything else? Anyone want to be different? So for every member that comes in, you call upon the hash function, and the hash function spits out the number. You compare it against in hash. In hash is the minimum of all hash values you have seen so far. That's the only thing you're keeping around, aside from that hash function. So how much space are we talking about? Constant?
Yeah, constant.
Okay, the answer is with this new approach, you're using as much space as it is required to store one real valued number. How big is one real valued number? The practical answer is, if you think the precision of a float is enough, that's constant. The theoretical answer is it's unbounded. Because keeping a real valued number requires perhaps many more bits than we have. Okay? So I'm going to be talking about one space saving trick that you can do quickly. Instead of storing in hash for real, I'm going to be storing in hash approximately. This time around, I'm only going to be storing just the count of trailing zeros. That's weird. Let me try to explain this. Suppose you hash an element, and this is what you get. What I'm going to be counting is the number of zeros before it becomes a 1. Assuming that the distribution is uniform, here's the thing that you should have in mind. What is the probability? This is binary, by the way. What is the probability that something is going to start with 0 and then go on to be whatever? About a half. What is the probability that it's going to look like this and then go on a quarter? So basically, this is as if you're flipping a coin until you see the first X, and then you count the number of flips before that turns up X. Okay? So instead of storing the actual hash value, what we're storing instead is the number of trailing zeros. The benefits of doing this trailing zeros is that you're only going to need much fewer bits. We're not storing the actual floats anymore. So how does it work this time? We're going to hash it just like before. But this in hash is actually the count of trailing zeros. The best one so far. So if The new hash is less than 1 over 2 to be in hash 2, which is what we're keeping. We're going to update in hash 2 to the 0 count of this loop. And this means that you're only going to need something like log long and while having the same amount of accuracy. We can increase the accuracy by running parallel copies of this thing and then do some kind of voting, combining all of the accuracy together, which I'm going to show you next. One great idea that is going to show up, and this is what people really use in practice, including in database engines and other data analytics tools, is what is known as hyperlog. So I'll get to that in a bit. But before we do that, let's talk about some rough intuition for why this works. So when we hash an input A, it has an equal probability to be mapped to any of the values in the range, right? Suppose n, for simplicity, let's say n is a number between 0 and 255. Which means that you can kind of think of this as a random experiment where we perform geometric trial. If you still remember something in math. The thing is, about 1 over 2 to the r fraction of a's, we have a tail of r zeros. But if you don't recall that, then we try to work out something for you. Let's say n right now, the range is 8. So what are the possibilities? Maybe it's going to map to 0. This is the binary. Maybe it's going to map to 1. Maybe it's going to map to 2. Maybe it's going to map to 3. Maybe it's going to map to, how do you say, 4? Not that way. I can't in binary. But anyway, let me fix that real quick. This is 5. This is 6. This is 7. And this yourself is very different here, right? When we generate a hash function, a value from a hash function whose range is 8. We fix this 3 bits. Now, there is an equal probability of it landing here or there or anywhere, right? Uniformity assumption. So what is the probability that your hash value is going to start with 0? As you can see, half. What is the probability that your hash function is going to have 2 zeros at the beginning? 1 over 4. So what is the probability that it's going to look like this? The first arm are all zeros. And then the rest is whatever. 1 over 2 to b, 1 r. This reasoning or like generalizing the system. And that's also reasoning. Therefore, if you saw the longest rail is r equal to 2, then it practically means we have seen about 4 distinct items so far. That's the probability of it happening. And if somehow the trailing zeros is such that the last of them is r, so maybe you need to have seen about 2 to the r distinct items before that happens, right? Basically, geometry reasoning. Which is why the way this thing estimates it is, at the end of the day, if you ask for what is the number of distinct element, is your output 2 to the we hash 2, which is the number of trailing zeros. So that intuition works to some extent. But if you want to show this more formally, then we can prove that the probability of finding a tail of R0 goes to 1 if M, the missing element is greater than 1 or 2 to the R, or it goes to 0 if M is less than 2 to the R. Therefore, 2 to the R will almost always be M, roughly speaking. What we just need to know is how many trailing zeros we have. And in the end, we can combine multiple estimators. So each one of these is going to give you an estimate of the distance count. In practice, people don't really implement this because you're going to need many copies of such estimators, and combining them is unpleasant. So there is a paper in the grand scheme of things, it's pretty recent, 2007, about as old as some of you guys in this room. And this is known as hyperlog law in today's literature. If the math before this made you doze off somehow, you can come back now because this is just a description of how it works. The idea behind hyperlog law is we want to be maintaining several copies of the previous estimators all at once without needing to actually do them explicitly. So for every element that comes in, previously we would hash it, right? And we would get a sequence of bits, and we would count the number of trailing zeros. This new approach is going to do the following. For every element that comes in, we're going to hash it still. For example, the first element that comes in, once we hash it, we get this thing. But we're going to use it in a different way. We're going to use the first key bits to set this thing into substreams. So originally we would have just one stream. But now for each element, we're going to hash it first, and then the first key bits will determine which stream substream is going to go into. Example, once you hash it and you look at the first 3 bit here, it says it's 101, so we're going to send it to substream number 5. If it hashes to whatever it is, but the first key bit says it's going to be 001, we're going to send it to substream number 5. So what is the picture now in the grand scheme of things? This is the big stream. And once you hash it, you're going to have a number of substreams. So an element is going to land on one of these substreams. One thing to note right now is if the element A shows up here, right here, and it was sent to substream 2, as an example. Later on, if A shows up, what guarantee do we have? We actually know 2 things. Number one, the hash function is going to return the same sequence of bits, which in turn means that A is going to be sent to the very same substream, right? So if we're using P equals to whatever, this means that the number of substreams in question will be 2 to the P. And for the purpose of this presentation, I'm going to be using the letter M to denote the number of different substreams. In a way, P controls the precision of this estimator. So very often, as we increase P, it's going to become more accurate. The question then is, for each of the substreams, what do we do? And this is where idea 2 is going to come in. we're going to process every substream like before. What did we do before? We keep track of one number per substream, and that is the largest trailing zero count, right? So we're going to do the same. In this case, this guy got sent to substream 5. What do? We look at the remaining bits, not the first 3, because those first 3 were used to determine which substream it is. This time, we're using the remaining bits, and we are going to count how many trailing zeros we have. And that number of trailing zeros is going to be stored inside the substream. The picture I want you to have in mind at this point is this. If I snapshot any moment right now, what I'm going to get for every substream is the highest zero count for that substream. For example, this guy might say my highest count is 5. This guy might say my highest count is 4. This guy might say 7. This guy might say 2. This guy might say 1. Right? So each substream has its own count. To get the final estimate, the actual distinct element count, we're going to need to combine these numbers somehow. Make sense? Okay, let's see what we do. I'm going to do this in blue. Basically says it's going to be 2 to that power. Okay. And for this guy, it's going to be 2 to the 4th. This guy is going to be 2 to the 7th. This guy is going to be 2 squared. And this guy is going to be 2 to the first power. But this time around, we have a lot of substreams, so we need a way to combine them all. What is a good way to combine all these estimates? High-parallel law proposes a scheme to combine them in a very clever way. The math behind it is exciting and yucky, so I'm not going to go into details. But roughly speaking, this is what happens. This first part says, what would be doing a harmonic mean of all the estimators? But it turns out, if you look at it from a statistics perspective, the expectation is not unbiased. It actually is unbiased. So we need some correction. And here is a correction factor. This correction factor looks ugly, but for practical purposes, we can think of this as going into NumPy and you get a simple number back, and that's the correction factor. So it's not that bad. We can even pre-compute it at the beginning. So, in terms of implementing this code, what do we need to do? Once we get all the estimators, compute all these, and then average them out, and then re-weight it. Right? And turns out, this is really good as an estimate for the distinct element counts. For some perspective, let's say we want to count 1 billion distinct items with 2% accuracy. It turns out that we're only going to need about 1.6 kilobytes overall. So that's just a tiny amount of space to track lots of distinct elements. That's how efficient distinct element is. The second portion of today's lecture, I should pause and take questions before I talk about the next problem. I will mention that most data analytics platforms out there, including the big name platforms that we talked about in the earlier term, have hyperlock law implemented in their code. So very often we can even call hyperlock law. guess a good test of understanding is this. Given what we have mentioned so far, if you were to be given a Python IDE and like a day to spare, could you implement hyperlock? What is it? You need 2% accuracy. I think this came up before, so I might as well try to settle it. Okay, let's say the true count is 100. If I report 102, what does it do? It's off by how much? Once again, there are often two ways to think about this. One is you can think about it in terms of, actually it's just the difference between 102 and 100, right? And in this case, you say the absolute error is 2. But usually when we think about percentage, we think about relative differences. So, how much is the difference relative to, relative to the actual value? It says what? 2%. In general, if you are into this kind of thing, there's a framework known as delta epsilon error. I'm digressing by the way, so if you don't want to listen to me on this part, you can zone out for 1 minute. But this actually is the model behind most of these algorithms. What this guy says is the following. If the true thing is x, and you have an estimator which is x equivalent, and you look at the difference, what does it mean for the error to be rather small? It means that this is going to be less than epsilon times the true thing. If you move this guy onto this side, this is exactly like computation right here. But like all these algorithms are probabilistic. So everything is happening in probability, right? So on this trial run, it turns out to be perfect. The next time you run it, maybe it's not as great. So how do we say it is going to meet this error condition most of the time? Here's where the delta part is going to come in. The probability of this being true. How do you say this being true? Well, in words, this is just as the error is controlled to be below epsilon %. That probability gotta be, what do you expect? Low or high? This is the good event, right? The event that the error is within the limit. So what do we say? We say that the probability must be at least 1 minus. So that's sort of the whole landscape of how most of these are modeled. And typically, if we don't say anything better, the delta is something like 5%. So we're thinking about 0.95 probability of success. And you can kind of boost this at the expense of adding more time to boost this. The second problem is, someone was saying that if you had to implement this, you still couldn't. What is missing? If you have to implement this version, can you? Before we go back to law, the one that just compute triple zeros and in fact value 0. And if you want the output, just raise 2 to that power. This is merge implementable. Are we facing a skill issue or something? What might be preventing you from doing this? What are your worries? Yeah, there's some things like that, and there's a recent paper called also a lot of. Oh wow! But we're not going to go there.
Not yet.
Not this term.
So you will stay in this term?
No, maybe never. Yeah, but like I'm asking this out of curiosity because this level of details, maybe hopefully should be enough for someone to implement it. If it is not, then I want to know how else it can be, what extra should be in there. But that's not very practical, you know?
I don't know what I'm facing right now. I feel like my
Fine. Okay. Maybe I'll stop trying on that front. I'll talk about problem 2 for today at least. And initially, you might be interested in doing something like this. Max count is, let's see, you are a router, a switch, whatever, and you want to find the element that has the maximum frequency. If that thing doesn't click with you, here is something easier to think about. You are a network switch, right? Everyone knows what a network switch is, I guess. Or a network switch at home. Anyhow, part 1 is going to win room. Part 2, Edie's room. Part 3, somewhere else, consoles, right? And there are 8 of them. You want to keep track of which room is the easiest. Because for every data, for every frame, just to use the right term, there is an address that comes with it. So we want to know which address is appearing most frequently. Make sense? Who is always popping? Or what is a very popular destination? What is the most popular destination? Can we do this easily? Yeah, sure, because we can keep track of all the IP addresses and we can track the frequency. This issue came up before, and if you want to do this, it will require how much space? Linear to the number of IP addresses. Also, however much you need to keep the count. And that's not very nice. What if I don't have that space? Buy a bigger router, buy a bigger machine, just put in the money and everything is fixed. In real life, there are situations where you actually want to track this in space that is less than linear. I got a bad news for you. The bad news is that if there are 2 competing locations, for example, let's say Microsoft and Google are equally popular, and they're off by just a few hours. It's really hard to distinguish between them unless you keep everything. Okay? So it turns out that distinguishing between repeated elements between maybe 2 choices is really hard. So instead, we're gonna try something easier. We're gonna try to find elements with frequency, which is at least total frequency divided by s as a subparameter that we choose. And the space that we're gonna need is gonna be proportional to s. If you took applied alpha, you saw something already, but I thought I'm gonna try something new here. And this is where the idea from last time is gonna come in. Oh, by the way, this very problem is known as heavy hitters. So we want to find on the top guy, like everyone whose frequency is in the top rank. So this is a paper from around 2004, 2005, as old as most of my guys from now. It looks something like this. It's known as count min from last time. Remember count min? Count min is an extension of Bloom filter that does the following. We are going to have W columns and L rows. If you remember last time, a Bloom filter is just one row, right? Every time an element comes in, you have a few hash functions, and everyone is doing action to the same way. And you only store 0, 1, so it's a bit array. This one is a counting bit, no longer bit array. You have a counting matrix. Count min from last time. Wait, no one remembers count min from last time? Works like this. We even have an animation for it. This time, let's say 2 shows up, right? Say 2 shows up. We're going to hash it how many times? L times using L different hash functions. That's why we have L different rows. If the first hash says it's going to go here, the second hash says here, and the third one says here, what are we going to do? We're going to bump the counter at those locations up by 1. If my animation works fine, it should say 1, 1, 1, 1, yes. And then what happens? You can observe the next guy, 5, let's say. It's going to send 5 to 3 different places, hopefully. And that's where you bump the count by 1. 7, sending happens. 5, sending happens. And 5 again, sending happens. Note that we're not interested anymore in listing count, so it's fine to be busy. The question is, at the end of the day, if I inquire the frequency of 2, what do I do? I'm going to apply a hash function to say L to look into those same places, 1, 2, 3. And it should return something. Which one? We know that every single cell in here, wrong kind of cell, looks like this. Either it is a true frequency of that guy, or it is the true frequency of that guy plus garbage. I mean, pollution from other guy. In this case, we want to get the minimum for that reason. Because the minimum one, the smallest one, is the least polluted of all. So you can trap, and you can actually read off all the frequencies. In terms of analysis, we said this already, it's the frequency of by 5 hashes 2 plus extra mass, which is what I call pollution. We showed last time that the expected extra mass is at most total mass divided by the number of columns. That's what we did in the report. In case you have heard of one of these names, you can apply what is known as Chef to show that this is true probability of this 1/2. Can't help myself. if you apply, if you set L to like log m, you get that the probability of this being true is close to 1. In technical term, high probability. Therefore, you can compute heavy hitters from the frequency of. And how many rows do we need? Somehow it works out to be W is S. Maybe there's a log factor creeping up, but log, who cares? What is M in this case? Number of distinct, sorry, practically string length. Like if there are M different elements, so that we first. I think we need to count everything, but I need to double check the calculation. Okay, I'm going to move on to a different presentation altogether. This is more than what to expect in the final stretch of this term. As you know, we have a final project component for the term. And this is different from assignments, all the assignments. So the theme of this project component is going to be, we want you to be using data engineering and data mining techniques to solve problems from the real world, either motivated by that or an actual real problem. You can do this in teams of, at most, 3 students. As everyone knows, coordination effort increases with the number of members. So oftentimes, if you have a team which is by yourself, you probably don't have any synchronization overhead. 2 is probably optimal. 3 is a bit weird, but anyway, you allow up to 3 students. Not including those.
So you really want to put it
Not including those. Here are some standard examples of what you might try, and these ideas are drawn from either Kaggle or towards data science blog posts. Anyway, you can find this list on the web. I'm not going to try to go over them. But if you can't think of anything else, maybe you can pick one of these. But I encourage everyone to first start thinking about what might be interesting to you. In terms of scope, because this is super vague, so I think I should give you some guideline or at least some thing to hold on to in terms of scope. Very broad, really. We just want you to use data engineering / data mining techniques to tackle a problem that you find exciting. Which means that this is supposed to be a fun endeavor and something that that is so that you can learn something new. But since it is part of the final project of a course which is 300 level, maybe we also need to make it sizable, meaning that it should be of a size proportional to the size of your team. A one-person project is not going to be hopefully not of the same size as a 3-person project. So what are the steps and expectations? I guess it usually begins with you choosing a problem that excites you and also convince people around you to also work on it. If you cannot find a common ground, maybe just do it by yourself or do something else. You also want to identify and gather data that you need, either sample data or some sort of syntax data generator that you can use to simulate the data. And then you want to look into how you are going to tackle the problem. Step 1, 2, and 3 should be done soon because there is a written proposal due. How many days? 2 weeks minus 2 days from now. So 14 minus 2 days from now. This is going to happen on campus. This is where I'm going to be sending a proposal. Between now and the due date, I'm going to try to meet with people so we get an idea of what's going on, and what might be feasible, what makes sense, and what is probably too ambitious or too simple. That part, for that matter. It doesn't mean that you cannot begin working on your project until the proposal is due. You can begin now. But the next step, logically, is for you to implement and evaluate your solution. The outcome in the end is something working, but then I can't really run everything, right? So I'm going to be thinking about asking you to summarize the process and results in a blog post style document, which is going to be preserved on your Git repository. And then we're going to have final presentations in the last week of classes, plus if that spills over, the final week, where some of you might have exams. In terms of what you have to deliver, obviously that blog post, which is going to be on your own repository. Oh, it's going to be part of GitHub Classroom, just like before. So everything is going to be tracked on there. Since this is a group project, and it will be kind of funny if you do it by yourself, you're going to have a peer review evaluation form that you have to complete. This thing has 2 parts. The first part is you will be reading over everyone else's blog posts to see what you think of their project. The other part is, in case you're not working by yourself, you should be evaluating people working with you as well. But if you're working by yourself, maybe you get to evaluate how well you're working with yourself. And then for the final presentation, you want to be up here with a slide deck. You can be spending around 15 minutes discussing what you're solving, what's the data involved, the method that you use to tackle the problem, give me a demo, and what result you're getting. I believe you actually do a research project. You have no problem with about 15 minutes with exciting content. And you are obviously going to be putting in your code configuration and everything except the data in your GitHub Classroom repository. I don't remember how much this is going to be worth in the total breakdown, but check the slide from lecture 1. But this is roughly how I'm thinking about grading the final project. Last I checked, they add up to 100%. you're using is, it doesn't have to be hard things, but like, if you're trying to solve something and it needs to be quite fast, but then you try to write code in a way that is not very exciting, and also there are much better ways it can be done without too much effort. That's where it might not be as high on that rating. Yeah, so I think usually this is the most exciting part because when everyone presents, you get to see all new, different, exciting stuff. In terms of lecture contents, we still have week 9, 10, 11, so 3 more weeks. We're practically done with analytics, so maybe you'll see much less of algorithms and cool ideas from the past, and more on how we can build data pipelines using tools. So we're going to be entering a new focus area.
And with this new focus area being the midterm?
No, because we're going to have only one lecture before the midterm. Right? The midterm, in case you guys do not keep track of time, is exactly 7 days from today.
Wow.
That seems reasonable, right? The question is the new data pipeline practical side of data pipelines that we want in terms? The answer is no, because virtually there's something between now and then in terms of data pipeline. There's no new lecture on that topic between now and the midterm. The midterm is next week.
And from today and everything before today is something.
Exactly. And I'm opening up for questions and comments regarding everything. So where is everyone on A2? Okay, I'm not gonna ask for like exact progress, but let's see like roughly. Would anyone in this room say that you are practically 89% done with A2? Introduce the way.
We can do it, but the performance is not good enough. As the expectation.
I think we kind of realized already that getting the code to run is this much effort. Getting it to run with good performance is probably triple or quadruple or even more, right? So really, the hard power A2 is not getting the code to run. At least that's how I think about it. But what I do recommend is for you to finish A2 end to end, meaning You can read in the file, figure 2 component 1, component 2, component 3, get all the things. Okay, and then start thinking about where in that code can be optimized further. Yeah. Why? You can calculate it. Let's say you have numbers, and you spread them equally on a number line between 0 and 1. What is the probability of, what is the expectation of the smallest one? It turns out it's not exactly that. There's a correction factor which is plus 1. You can actually work it out, it's just one single integral. That why the thinking here is the and you're gonna have 0, 1, blah, 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 so on. And how long are you gonna process it? You are gonna take this implementation 1, and you are gonna look for what you can vary and the data set that you need some very careful to understand this is what I have so far with regard to this topic.
I didn't print it out for
Pretending that you can see my one app and it happens to be actually at a smaller deck and then that's kind of like so previously it shows up here if you have one step one
so this is like a segment.
Well, if you can meet this number, awesome. That's why I said want something. So like yeah, it's kind of nice. I have comments. Number one, this baseline is not fast enough. But you can compute stuff like and number two, okay, well,
I just recently changed my but the local market why not just over there?
But it could be a lot. Then you can't really attack this thing, but then you have to do except one the best thing ever. Almost one second. Assuming that the rest can be done.
And then the problem is because Polar is implemented so that like it makes user in Python. The document for it's absolutely shit. It's a lot.
Right? Because the way so unless you want to extend or you want to be someone who can
So I spent way too much time just writing it, and even the example and the documentation is sometimes more like everywhere is not good at it. No, I thought it's so much. So just today I need to kind of like a specific role that was like I wanted to use, but I couldn't find it. Maybe it was like that,
in terms of math, no. This right here. This is not okay. This is string better than this. I want you to find the expectation. What does it mean for something? If X is the if they're M, they're just and it means that every one is X. Sorry, there is one person who is X. Everybody else is at least X. Go ahead. Or maybe it helps to think about it this way. What does it mean for the expectation to be at least X?
คือแบบแทนที่จะออกมาเป็นแบบคือสีที่ผ่านมา
ตอนนี้กูมาสอนตัวนี้ถ้าถึงจะเป็นแค่สองเราไม่ถึงแล้วมันพอมาที่เป็นเจ็ดเจ็ดแล้วคิดว่ามันจริงแล้วผมไม่ได้
แต่ต้องออเดอร์ตามเราเลย
ที่เมลที่เขาหลายสายที่เราไปทำ
ถ้าถามว่าที่อีเมลที่สุดทำแล้วก็เราจะทำอะไรส่งเมลไปไหนเพราะว่าสิ่งที่เราต้องทำ
ได้เลขที่แบบต่างก็ควรจะอยู่ใน
Otherwise, you would have the road but there are two road access. One is the original road access, the other one is the road access.
ก็คือตอนเราเอ็กโซเทชันก็คือ
บอกว่าเขาเอาไปจาก presentation เนี่ย25ไม่ใช่กาแฟเย็นเลย
Yes, but they keep on touching all the sense. I don't know. There are things that people think are common sense. Turns out to be less common. You mean like for every document, once you generate it, you keep that somewhere.
Right next to one time.
Correct. Okay, I have a good answer. If you have anywhere in memory where you store all the scrolls, that's going to be a lot of memory files. So you want to kind of compress that and move on to the next step without really storing explicitly the whole list of scrolls.
How do you compress it?
How do you compress it? You hash it.
Using the
Using whatever the heck hash function is like. Char is slow. Char is easy slow.
That would be more permutations than
What?
the combination อาจารย์
ที่ผมกำลังเจ็บอะไรอย่างนั้นมันเกินที่ทั้งสองก่อน so hashing with hash crazy is it
ถ้าคุณมาที่ผมกำลัง
I got a question for everyone who has studied probability. And maybe if you didn't, especially if you did several stuff as well. Shall one? How many days? One. Shall one?
สอนไปนั่นแล้วอ่ะช่วงสอนไปแล้วอ่ะเมื่อก็ like last week อ่ะวันทูแล้วเนาะ
If my memory serves me right, and I may be wrong on this, it's something like 160 minutes.
รอบเช้าก่อนรอบเช้าไม่ได้
But whatever. I could be wrong. Never mind. The thing is, you can think of shower as a function. And you can feed it in a history. Did you ever worry that like you were from Ubuntu.ISO yesterday and this guy is Ubuntu.ISO from 5 years ago who had to reach out despite it hashing a super duper large universe onto just a few bits. Yes, collisions would happen, but even though the universe is super large, the actual number of strings you have in your data is tiny. So the chance that two things in your bucket will hash the same number is practically you can compute it, but you'll find out that like that probability is not what you're about. So it's 32, probably fine. You can even begin with something for it.
อันนี้หมายถึงเวลาแฮชหรือว่าอะไร
Both.
อาจารย์แอนฟอร์อะไรสรุปแล้วคือแบบมันจะควรจะเป็นแบบไหนแล้วแบบตามเป็นแบบไม่ต้องมีแบบ
Okay,
like pivot hash คืออะไรไม่ใช่ยังถูกแต่เราวิจัยไปเราแบบสมมติเราได้ออกมาแล้วแบบได้คือแบบไม่ควรจะแบบแบบเป็นก็แบบ
anyway อาจจะคงตี
ไม่ใหญ่เลย
how long is this vector?
I have no idea what the heck
It should be every time you hash it, you get a number. So the length of the vector should be as long as the number of so it's linear in the size of the vector.
มันก็ประมาณนี้แล้ว
Can you do something like the vector is sorted already? So okay, that's one idea. I have another idea. I'm a very lazy person, right? So I don't care if my sense gone duplicate items. Every time there's a new thing, add it.
เห็นแล้วก็ศูนย์
Every time there's a new thing, add it.
นักวันอยู่ที่ไหน
For sure, by the time I'm done, I'm gonna get a lot of At that time, either I'm gonna try to do a half set or I'm gonna sort it completely out.
มันจะทำ
เยอะต่อในเรื่องนั้นจะต้อง
Then the organization
วิชา optimization
the one you said like restore unique items.
แต่แล้วมันเป็นแท็กไม่ใช่เหรอ
They can be combined.
ที่เขาที่แคชคือหลอกแล้วเวลาเปิดแล้วก็มีคอนดิชันด้วยแล้วก็ตัวแต่ว่าตัวนี้เป็นตัวของสำหรับชิ้นก็คือ
Or you guys gonna ask something?
The regular signature matrix, right? The resolution itself should be up always updated and right should be default. So like your one password like when you hash this some value and then you save that with hash value. And then right now the problem is in my code there's some for some documents right the hash value is set to maximum. Which means that it didn't get updated. Which theoretically should not be possible.
I feel like that's about because as you go through all the documents and you go through the different chapters, it should be updated. Unless the document is missing.
Yes, I want to say something, but I don't know how to spread like the email for 8K.
Much smaller data set. Maybe an email with one email with 2 words in it.
Oh. Would be interesting.
There are two almost orthogonal angles, right? One is directness, the other one is performance. Your code can run super fast, be wrong, and that's why we use it. And your code can be super correct, but like super slow, then that's also not gonna fly. So you want to be slow.
So there's a chance where the data set or email has nothing like from the like from to subject and then to what and then
มันมีบางอันที่มันไม่มีเจอแล้ว
There's a chance that the email is outlandish, and you kind of want to return the hell of it. But there are two separate concerns, right? One is your code is buggy, and there is shitty email there.
I can tell you right now there are some email without 2 and there are some email with 2 email with like more than 1 line. More than 1
But you want to have it use for both because I understand that the data set is not good at all. Yeah. So for both, what you want to do practically is sorry.
The reason I wasted so much time doing that because I was trying to get like 4 separate like vectors from like one iteration. No, I was able to do it with the point if I know that I was supposed to combine them, then I wouldn't have that problem in the first time.
So yes, please.
No, I don't. If I don't do that, this is like a OP การ
คือตอนนี้มันมีปัญหา
กูไม่หา
ก็คงจะสร้างความชัด ที่ดูสิวันนี้
ไม่แต่ว่ามันถ้าเกิดมันร้อนเพราะว่าร้อนแล้วก็สื่อเพราะว่า let's say you have to choose attributes and there should be kept in a vector, right? In one of the ways, one is you have two vectors, one for attribute A and the second vector for attribute B. Another way is to have a vector of a struct so that A and B together, right? Depending on your access pattern.
ข้อบัตรเรียนคือ
มีของอันหนึง first name last name and to and from. For example, you can either have a vector giving all the truths and a vector giving all the froms, right? And they can link together, right? Indexes. Indexes two mean that email ID two is that, from is that, right? And that leads to super ugly code. I mean, it just ruins your brain. Also, it's really bad for cache.
ต้องการอะไรที่เรา
ถ้าต้องทำเองI กับเดียวไปมันจะได้สองอันนี้ว่ามันจะ access แบบเป็นแรงมาก What's up?
How do I know if I'm doing the right thing? So I just get and then it up to and then you compress it by hash. You can do that. And then you dictionary each hash is very
You second.
กินด้วย
So you hash that and then you get a bunch of
So then you put it in the dictionary.
What are you going to be using the dictionary for?
That's for the communication dictionary.
Okay. Are you actually using it?
Find a way to keep vocab so
Once again, conceptually, it's a dictionary, but that hash function serves as a dictionary already. The only downside to using a hash function this way is if you see 3 later on, you have no idea what it is. It's one way thing. You can go from singles to a number, and you can go back to a number. So the only reason to do it if you care to have that mapping is so that you can reverse mapping. Sorry, integer back to ahead of time, I can tell you that that reverse lookup might be useful when you are looking. Like you found that this form was like this. What is it? But once you're done with the whole thing, that reverse mapping can just go down the drain.
So if I have that hash option, let's say, should I just put it like this, what would make sense?
Why not?
And it's just
A quicker way is probably because all these are numbers. You can every time you generate it, keep it in a vector or something like I mean this. Yeah, and just do it, redo it.
that is faster than this.
That issue is faster. And yeah. Keep in mind that one recommendation I have at the very top of the design is wherever you can make it a which means that all these processes can be done in parallel. How do you deal with it? There is nothing such as you're writing it yourself.
But then you still need to check like
There is no way to be too fast than ON because first of all you have to touch all the data. So ON is the right target.
ก็คือมีอยู่ที่เก็บไว้
What I'm saying is it's faster than incrementally adding each element on the set one at a time.
So like it parallel, you just line the element and make a patch.
ก็ใช้
And
ได้
there's like patch.
Technically, all these can be done at the same time.
Yeah, and then
But if you think that that is too fine grained, you can say, okay, I'm going to cut this up into 5,000 pieces, however many pieces. For each one of them, do that, and then merge at the end.
so just expand each of them
Yeah.
and then we can do
Yeah.
that.
You need to be good at it. The nice thing about not picking a set is you know practically where this guy is writing to. Because if you were the second single, you can always be writing a array slot number 2. As a set, you need some kind of recurrent set, otherwise you're not be writing recurrently to it.
This one,
It will use some amount, but the trick is you can process them in batches. This is the first however much, and then move on. What options do you have to use something? CPU, practically you can either sort it, and there is good parallel sorting algorithms. You can throw that thing into a big hash table. There is also a parallel hasher that you can do, and then read it back out. But we're not being generated a matrix ever.
So you like spouse
Those NPCs are only for conceptual thinking. And I'm not surprised this is the first time I saw him in a while.
I only just start there. I was in
No, no,
no, I was in last class.
No,
last maybe
that pointer is too long for me to trace. Maybe you were in the spirit. Do you guys want A2 and A3 conversation? Let's go up. Let's up this one for and take a while, but do you really need it? Let's go home. I mean, my